In this section, we're going to take a look at the concept of variation of parameters. Up until now, we've had the method of indeterminate coefficients to find a particular solution to a non-homogeneous problem. It has an advantage. It's useful, it's efficient, but of course it has a pretty glaring disadvantage. It's really kind of limited, because the only times we can use the undetermined coefficients method, regardless of whether we're using the annihilator form or whether we're using the superposition approach, either way, you're limited to linear equations that have constant coefficients, and the input function must be either polynomial, exponential, sine, or cosine. But what if you don't have that? Okay, so now we're going to take a look at a more general method where these assumptions are going to fail on us. For this section, we're still going to consider constant coefficients, but we're going to now remove the restriction on the input function. That is to say, what our equation will equal to will not just be a polynomial, an exponential, or a sine or cosine. Okay? So in order to motivate this, we're going to take a look at a now already solved problem, something we've already seen before. Let's say I have y prime plus pxy equals f of x. Okay? Here's a first order problem in standard form. Okay? All right, well, we saw this all the way back in chapter 2. We did this by an integrating factor, right? Here we said, okay, we have an integrating factor. And that integrating factor is what we called mu, and we found it by taking e to the integral of this coefficient function here with respect to x. And what do we do with it? Well, we multiplied by it. That's why it's called an integrating factor. It's a factor. You multiply by it. So here what we got was mu. In fact, let me not write it as mu. Let me write it in its exponential form. E to the integral px dx times y prime plus px times e to the integral px dx times y equals e to the integral px dx times f of x. And hopefully you remember that the reason we did that was because that makes this left-hand side into just the product rule. This is the result of taking the derivative with respect to x of that integrating factor times your unknown function y. So this would be d dx of y times e to the integral px dx. And of course here you would use the product rule. You would take the derivative of the first times the second plus the first, the y, times the derivative of the second one here. And of course on the left side I just leave that alone. E to the integral px dx times f of x. Okay. But then, since this was just a derivative, we could now integrate it. We would say, okay, so now if you integrate this with respect to x, well, then you'd integrate this side with respect to x as well, and you'd end up with just the stuff on the inside. The integral of the derivative is just the inside. So we would get y, e to the integral, px dx is equal to the integral of all of this stuff plus some constant of integration. Integral of e to the integral px dx f of x dx plus, of course, some constant. And finally, to solve for y, we would do this. We would get y equals, let's see, when we divide by something with a power, that's the same as multiplying by something with a negative power, right? If I have x to the power 5 and I divide by it, that's the same as saying x to the power minus 5. Right? Dividing by something with a power is the same as multiplying by the same thing but with a negative power. So here I'm going to go ahead and move this over. I'm going to divide it to the other side, but instead of writing it as division, I'll write it with a negative power. So here I get y equals e to the minus integral px dx times times the integral of e to the integral px dx f of x dx plus some unknown constant c1 times, again, e to the minus integral px dx. Okay. And this is our formula for solving a first order problem via an integrating factor. Now, some of you might look at that and go, wait a minute, I remember doing integrating factors. I remember solving first order problems. Those were nice back in chapter 2. I don't remember this formula. Yeah, that's right. We never derived it. You say, well, then how did we solve if we never had a formula? We used the integrating factor. Right here, you see one good reason why we don't have a whole lot of formulas in this course. We have techniques instead of formulas, because the formulas themselves are huge and really awkward. It's e to the negative integral px dx times the integral e to the integral of px dx, no negative, times the input function dx, plus some constant e to the minus integral px dx. Those get really, really complicated. And keep in mind, this is a first order problem. So this is the reason we don't really see a lot of formulas in this course. We see techniques. The second thing I want to point out here is that even in this very early problem, look what you have. You have a non-homogeneous first order problem, which has a single parameter, a single unknown parameter here. That means this is our y sub c. This is our complementary solution. And then here, there's no unknown parameter. There's no C1, C2, C3. So this is a very specific solution with all known values. That's what we call a particular solution. Even way back then, before we knew anything from chapter 4, we had that, hey, look, first order non-homogeneous problem has a single parameter complementary solution plus a particular solution stitched together to form its general solution. Even back then, we had that pattern already existing. You say, okay, but, well, what's the point of this? After all, we already know how to solve something like this, so what's the point of creating this more elaborate formula? Is this really something we're expected to remember? No, not at all. This is not meant as a new formula for you to remember. You already know how to do this in a much simpler, more efficient way. No. This is meant to point out something interesting. Notice that your complementary solution is a single parameter times this function here, and that your particular solution is that same function times some integral. Right? That's not for any specific function. I mean, this p of x, we never said what it was, nor did we ever say what f of x was. Notice that your particular solution is not completely separate from the complementary solution. They're different in nature. This one has an unknown parameter, whereas this one doesn't. But they both have this same integrating factor, or almost integrating factor, right? It's got a negative there, within its factors. So does that mean that y sub c has components that can be used to find y sub p? Yeah, that's exactly what it means. So now suppose that we find some solution of that equation. Suppose we'll call it y1. Suppose y1 is a solution of our starting equation y prime plus pxy equals f of x. Okay? Well, what that means is you should be able to plug it in. Okay, so that means that the derivative with respect to x of y1, I'm plugging it in right there, plus pxy1 is equal to, sorry, I want to concentrate on the complementary solution. So that means I should not be focusing on the original problem. I should be focusing on the associated homogeneous problem. Okay? So let's suppose that y1 is a solution of the homogeneous version of this, the associated homogeneous problem. Okay. All right, well, then that means that if we take that y1 and plug it in, we get, well, the derivative of y1 plus px times y1 should equal to 0. Okay. Now, it's easy enough to show that this factor works here. Like, you can actually just do that. Like, take this, plug it in, and you'll get 0. Since e to the minus integral px dx works as a solution, then we get our general solution is just this constant times our y1 let's see. That would not be our general solution. That would be our complementary solution. Then our complementary solution is C1Y1, and our particular solution is, well, that same y1 times something else. And our particular solution is y sub p equals that y1 times something else. Now, that something else is not a constant. It's some function that you get by integrating the exponential of the integral of p times the input function. Okay, so that is definitely not a constant. It's a function of x, it looks like here. So it'd be y sub p is equal to u times y1, where all of these are functions of x. In fact, I should even write that. It's equal to u of x times y1 of x. Okay. All right, so what? Well, so if this is a particular solution, that means we should be able to plug it into the original equation and have it work out. Okay, so let's give that a try. Okay, so let's see. If my y sub p is equal to, and I'm just writing this a second time, u of x times y1 of x, then my first derivative would be, I'd have to use the product rule here, so it would be what, u1, sorry, not u1, u of x times, I guess I would want the derivative of y1 with respect to x, plus, and then I would leave the y1 alone and multiply that by the derivative with respect to x of u, du dx, like this. So when I plug that in, I would get, let's see, what my original question was, y prime plus pxy equals f of x. So y prime plus pxy equals f of x becomes, let's see, there's my y prime, so I get, let's see, I get u of x dy1 dx plus y1x du dx plus p of x times y, which again, y is my u of x, y1 of x, u of x, y1 of x, and that is equal to our input function f of x equals f of x, like that. Okay, now let's see. Here I've got u of x is a common factor in two of my terms. Okay, so what I'm going to do is I'm going to regroup this a little bit, and I'm going to have u of x times, and let's see, if I factor out u of x here, I get dy1 of dy1 dx, and then from this one I would get pxy1 of x plus pxy1 of x. Let's see, plus, and then this one right here is not included with these, so I'll leave this one alone. y1 of x du dx is equal to f of x, like that. But now we get something interesting. Hey, look, the derivative of y1 plus px times y1. Sorry, what was y1 again? Well, y1 was a solution of this associated homogeneous problem. So if I plug y1 into this problem, I get 0. Hey, that's what I've got. I've got y1 prime plus px times y1. That's got to equal to 0. So this term goes away. I'll say that again. y1 was introduced here as a solution of our homogeneous problem. It was basically the solution in our complementary solution here. So when you plug y1 into this problem, it should solve it. It should equal to 0. That's what we get here. If we take y1 and take its derivative, plus px times y1, that equals 0. So this goes away. And so you just get y1 of x du dx equals f of x. So y1 of x du dx equals f of x. And now keep in mind that what we're looking to solve here, we're looking to find what your u1 is. Because, well, our particular solution is u times y1. But we already know what y1 is. It was a solution to the complementary portion. It was a solution to the associated homogeneous problem. So if we can find u, we can multiply it times the y1 that we know to find our particular solution. Oh, but there it is. There's u. So I can go ahead and take this, divide it to the other side, and I can separate my variables. Here, by separation of variables, I can write this as integral du is equal to integral of f of x over y1 of x dx. Separation of variables. By separation of variables. But now that's, well, the integral of du is just u. So that gives us that u is equal to the integral of f of x over y1 of x, integral of the whole thing, dx, which means our particular solution is now predictable. Thus, y sub p is equal to u times y1. Okay, well, u is this thing right here. So it'll be u, which is the integral of f of x over y1 of x dx, times y1, which I'll put in front, because if I put it in the back, it looks like it's inside the integral. So that'll be y1 times the integral of f of x over y1 dx. Thus, our general solution, therefore, our general solution is going to look like y equals our complementary solution plus our particular solution, which we now have here. That is to say y sub c plus, well, actually, let me write that using the y1 that I have already. So it's going to equal to c1y1 plus y1 times the integral of f of x over y1 of x dx. Notice that y1 is this term in our complementary solution without the parameter, just this variable part. So if you take your input function, divide by your term from your complementary solution and integrate, and then multiply by that once more, that gives you your particular solution. So these are here, and this is just your input function. We can actually generalize this to higher order problems. Here, I do it with a first order problem because, well, frankly, this is already big and clunky enough to work with in just first order. That was not a short computation there. So that's why I illustrated with just first order, but this can be generalized into higher order problems. And this technique that we use of taking the parameter, removing it here, that one parameter C1, by removing that parameter, looking at just Y1, and then using that to find a particular solution, that's a technique which we call variation of parameters. So technique. Variation of parameters. All right, so we're going to go ahead and look at second order problems here. This does work for higher order problems, third, fourth, fifth, and whatever you want. It's just that as the problems get bigger, the variation of parameters technique takes significantly longer. So for a first order problem and a second order problem, the length is really manageable. Third order, it gets a little bit big. Fourth and fifth, it gets even bigger, and so forth and so on. So this does have a huge advantage over the last two techniques that we've seen in that it is much more general. Notice, we don't need f of x to be any particular function. Any function at all will do. The big disadvantage, and the reason we teach the undetermined coefficients method first, is because, in spite of the fact that this is much more general, it's also much longer to use, and it gets long really pretty quickly. So we're going to start by illustrating this technique for second order problems, and it does work for higher order ones. It's just going to be much longer. All right, so here, technique. To solve something that looks like y double prime plus pxy prime plus qxy equals an input function f of x. No restrictions on f of x right now. right? This can be any function you like. We're going to go ahead and, so first of all, it does have to be in this form. If there was anything here, you have to divide by whatever's here to make sure this starts with just y double prime. Okay? So here we're going to find the complementary solution. So step number one, we're going to find y sub c, which is c1y1 plus c2y2. Okay? Your parameters c1 and c2, along with the elements of the fundamental solution set y1 and y2 are going to go there. Okay? Next, you're going to go ahead and find the Wronskian. Compute w of y1, y2, which, if you remember from the beginning of this chapter, the Wronskian is just, you're going to take those two elements and write them in the very top of a matrix, and then underneath that you're going to have their derivatives, y1 prime, y2 prime, and then you take the determinant. Okay. Now, step number 3, you're going to compute two other related Wronskians. You're going to compute what we're going to call W1, and you're going to compute what we're going to call W2. W1 looks like this. You're going to take the second column and leave it alone. Leave it the way it was, y2, y2 prime. But the first column, you're going to have a 0 on top and the input function on the bottom. It's called y1 because you replace the number 1 column. W2, you're going to do the same thing, except instead of replacing the first column, you're going to replace the second column. So we call this y1, y1 prime, and then over here we have 0 and f of x. Remember, all these have to be square matrices, so if you've got two elements for a second order problem, then you're going to just take the first derivative so that you have two rows to match your two columns. Okay? So we're going to find all three of those. Find your Wronskian. Okay, and then once you have that, you're going to find this W1 and W2. Okay, next what you're going to do is, notice over here that in order to find this u, we had to take the input function and divide it by y1. Here we're going to do something similar. We're going to divide and integrate, but with a first order problem, it's sufficient to use just the input function on its own. But with higher order problems, since you have more elements in your fundamental solution set, it's not sufficient to use just a single one of them. You have to combine them together, and the way that you combine them is with these matrix determinants. So here it's going to be u1 is going to equal to the integral of w1 over w. So it's like your input function over your element of your fundamental solution set, except here you have, well, you have more than one element. Okay, so then you put it together in the Wronskian. Oh, so that's why that w goes on the bottom. And then on top, you have to put your input function. Oh, over here in your Wronskian, you put your input function, and that's why that's in the numerator. You're going to take your u1, that's going to be integral w1 over w dx, and your u2, because you're going to need a second one because you have a second order problem, that's going to be, well, you probably guessed, w2 over w dx, like this. And finally, you're going to find your particular solution. Oh, I guess not finally, because this is, we do need to put it together with the original. So next we're going to take our particular solution, and that's going to equal to u1 times y1. So whatever you get here is going to get multiplied times the original y1 from the complementary solution, plus this u2 you get from here times this y2. And so finally, your general solution is going to be c1y1 plus c2y2 plus u1y1 plus u2y2, where the u1 and the u2 are these, and this y1 and this y2 are the same as they were in the fundamental solution set. All right, so you can clearly see a benefit to this. There's no guessing. There's no indeterminate coefficients. Everything is computed directly. No guessing, no fumbling around, no annihilating and then backtracking. You do exactly what you need from the beginning. The downside is these integrals, well, we took Cal 2. Right? I took Cal 2 as a student, and integration isn't always easy. So the bottleneck here, the part that's going to make this complicated, is twofold. One, these integrals are not always nice. And two, you're looking for a determinant here, and a determinant here, and a determinant here. For a 2x2 matrix, that's pretty easy. Multiply those, minus, multiply those. Same thing here, same thing here. 3 by 3, 4 by 4, 5 by 5. That gets really big really fast. Okay? So we're going to stick to second and third order ones here, but do keep in mind this can get bigger. All right, so let's go and take a look at an example of using this technique to find a solution. We're going to solve y double prime minus 2y prime plus y equals e to the x times the arctangent of x. We're gonna start off big, real quick. We haven't seen tangent, let alone arctangent. Here, the reason we have variation of parameters is because the previous techniques were not general enough. Here, we needed this to be either e to the x, sine x, cosine x, or polynomial of x. Now it can be just about anything. Okay. So here we go. First of all, we're going to find our y sub c. Okay. And we do that by considering the associated homogeneous case here. We're going to solve y double prime minus 2y prime plus y equals to 0. And that's simple. Consider the auxiliary equation m squared minus 2m plus 1 equals 0. That factors as m minus 1 times m minus 1. And so here we get two solutions. We get m1 and m2 are both the same number. So putting all this together, we get that our complementary solution, y sub c, is equal to c1 times e to the 1x, and then plus c2, the same e to the x, but now we're going to multiply that times an x. That's what you do with repeated solutions to an auxiliary equation. Okay. All right, so now our next step is we're going to compute our Wronskian. Right? So now we're going on to find our y sub p. And we're going to start off by finding w, which is the determinant of. So now you're going to take these two elements from the fundamental solution set here, the e to the x and the x e to the x. Don't worry about the constants, just the functions here. E to the x and x e to the x. And now, since you have two columns, now you're going to need two rows. You've already got one row, so now the second row is just from the derivative. The derivative of e to the x is e to the x. The derivative of x e to the x uses the product rule. Take the derivative of the first one, that's 1, times the second, e to the x, plus, now take the x, leave that alone, and take the derivative of the e to the x. So that's e to the x plus x e to the x. Okay? So I get e to the x plus x e to the x. And when I take that determinant, well, let's see, that's e to the 2x plus x e to the 2x minus, and then when I multiply these, I get x e to the 2x. Oops, x e to the 2x. And since those are opposites, they cancel out, and you just get your Wronskian of e to the 2x. Okay. Nothing too painful with a 2 by 2 matrix. Our next step is we need to find this W1 and W2, which are essentially the Wronskian, but with individual rows replaced by 0 on top, input function on the bottom. So W1, you replace the first row with 0 and your input function, e to the x arctan x. Second row stays exactly as it was before, x e to the x, e to the x plus x e to the x. Okay. If you multiply those, you get 0. Minus, if you multiply those, you get x e to the 2x arctan x. So here we just get negative x e to the x, negative x e to the 2x arctan x. And then W2 is almost exactly the same thing. We're going to replace the other column. So here the first column stays as it was in the Wronskian, e to the x and e to the x. But then over here I replace this with 0 and e to the x arctan x. Okay, so now if I multiply these together, I get e to the 2x times arctan x, and then minus 0, which I think I'll just leave it the way it is. Subtracting 0 doesn't do anything. So I find my w, and then I find my w1 and my w2. Again, with a 2 by 2 matrix, none of that is terribly painful. Now comes the part that can be challenging. Let's go ahead and integrate. Okay? Depending on the problem, this may or may not be challenging, but be prepared for this to take a few moments. So here, u1 is going to be the integral of w1 over w, which is the integral of, let's see, w1 was negative x e to the 2x arctan x. And we're going to divide that by our Wronskian, which is e to the 2x dx. Here, these two divide out, and we're left with just the integral of negative x arctan x dx. And that is integration by parts if I've ever seen it, right? It's the integral of a product. Now, normally, when you use an integral of a product and you use the integration by parts, you would say, well, x is going to be my u and the rest is going to be my dv. Because when I differentiate x, I get 1. And so it gets easier to do the problem. There is one exception to that, and that is when you have an inverse trig function. An inverse trig function should take priority over anything else. Because when you take the derivative of an inverse trig function, it stops being an inverse trig function, or even a trigonometric function. It becomes either polynomial or radical, depending on which one you're looking at. And that change is significant. So here we're going to do integration by parts. We're going to say, we're going to say u is equal to, I'm going to use my arctangent of x as u, arctan x, which means du is going to be the derivative of the arctangent of x, which, thanks to Cal 2, we know that's 1 over 1 plus x squared. Some people say x squared plus 1. That's fine, either way. 1 over 1 plus x squared dx. And so dv must be my negative x dx. Negative x dx, which means v would be the antiderivative of that, giving me minus 1/2 x squared. Okay? So when I integrate, I get u times v, that's negative 1/2 x squared arctan x, minus the integral of v times du. The two negatives will cancel, right? Minus a minus, that gives me a plus. The 1/2 is constant. I can pull that to the outside. And here I've just got x squared over 1 plus x squared. Dx, like that. Here I can integrate this separately. This is already done. I can integrate this separately. And let's see, that's going to give me negative 1/2 x squared arctan x plus 1/2 integral of, right here what I'm going to do is I'm going to add 1 on top and then subtract 1 on top. The 1 and the minus 1 just cancel. But if I don't let them cancel, I can now split this into 1 plus x squared over 1 plus x squared, which is just the number 1, minus the remaining 1 over 1 plus x squared. And now that's easy to integrate. This will give me, let's see, I've got a minus 1/2 x squared arctan x plus 1/2 of, if I take the integral of 1 with respect to x, I get 1x. And if I take the integral of 1 over 1 plus x squared, I get the arctangent of x again, with a minus in front. Arctan of x. Plus a constant. However, here we only need a single function u. Right? We're looking for u times y1. Since we don't want any, since we don't want any undetermined parameters in our particular solution, here this is technically plus c, but now we can go ahead and pick whatever number we want for c, because any one will do. Right? As long as it's an antiderivative of this, we're fine. And so here we will just pick 0 every time. We only need one u1. Right? We don't need a bunch of these. We don't need a whole family of them. So here we'll pick c to be a specific number, and we will pick it to be the easiest number we can come up with. That is to say 0. u1. So we pick c equals to 0. You say, what if I pick some other number? Would that be wrong? No, you're just writing extra stuff that you don't need to be writing. It's not wrong, though. And there we go. There's our u1. Here, I notice that I have, I can combine the like terms here. So I've got a, let's see, minus 1/2 arctan x Right? If I factor out minus 1/2 arctangent of x, I'm left with x squared right here. Over here, if I factor out minus 1/2 arctangent of x, I'm just left with 1. Plus 1/2 x right there. And again, plus c, but I'm not going to worry about the plus c. Okay, now we have to find our u2. And again, u2 is the integral of w2 over w. w2 was e to the 2x arctangent of x. E to the 2x arctan x divided by, and then our original Wronskian up here was e to the 2x dx. And since these cancel, I get just the integral of the arctan x. And this is also integration by parts. Some of you who don't remember your Cal 2 as well as others may say, well, wait a minute, that's only one factor here. I thought integration by part had to be the product of two things. Up here it makes sense because it's x times arctangent of x. But down here, there's just a single function. Yeah, but you can also think of this as arctangent of x times 1, which is true, and that's a product. Here, arctangent of x, we're going to go ahead and use that as our u. U is going to be arctangent of x, which means du is 1 over 1 plus x squared. This 1 right here, or you can also think of it as 1 dx, that'll be our dv. dv is going to be 1 dx, which means v will equal to just x. And so now by parts, we get that the integral of the arctangent of x is u times v, that'll be x arctan x, minus the integral of v du, that'll be x over 1 plus x squared dx. This part right here we can do by a substitution. Right? Here, if I notice that the derivative of the bottom is 2x, that's what I have on top. You say, well, no, you just have 1x. Okay, so we'll put a 2 there, and we'll put a 1/2 out here. The 2 and the 1/2 would cancel. But if I don't let them cancel, hey, look, the bottom has its derivative on the top. When I integrate something like du over u, that's a logarithm. So here I end up with x arctan x minus 1/2 natural log of 1 plus x squared. Again, plus a constant, but since we only need a single u2 as well, we're going to set that to the simplest number we can think of, and that's 0. Again, it's not wrong if you pick a different number, but that's the number we're going to go with, right? It's just the easiest one to work with here. Okay, so we've got, let's see. So we're done. All right, we've got our u1 and our u2, and so now we can find our general solution. Remember that our general solution y is equal to y sub c plus y sub p, which, well, we know what our y sub c is. We found that at the very beginning. That was c1 e to the x plus c2 x e to the x. Let's see, c1 e to the x plus c2 x e to the x plus, and now to find our particular solution, we're going to go ahead and take our y1, which is the e to the x, and we're going to multiply it by our u1, which our u1 we found earlier was all of this stuff. So let's go ahead and write that out. That'll be minus 1/2 arctan of x times x squared plus 1 plus 1/2 x plus, and then you're going to take your y2, which is the x e to the x, and you're going to multiply it times your u2, which was x arctan x minus 1/2 the natural log of 1 plus x squared. For those of you who are wondering, wait, I thought integrals of logarithms always had absolute values. Remember, your solutions have to be continuous, and if you have an absolute value, that causes issues because the logarithm isn't defined at 0. So here we go ahead. Oh, actually, I take it back. Here, you could put absolute values here because this is always positive anyway, so that you never run through a discontinuity. So because this is never negative, it's always positive, you can put absolute values, unlike what we usually would leave them off. But since it's always positive, the absolute value signs are redundant anyway. So either way, we're not going to put them on there. And so here we have our solution. And finally, we can go ahead and distribute and see if there's any like terms we can combine. Not really. Yeah, that would be fine right there. We'll just leave it like that. And this is our general solution, which that is not something we would have found by an annihilator. That is not something we would have found by any method of indeterminate coefficients. We find it directly, even if that direct path is maybe not a short direct path. Okay. Now we're going to take a look at one more example. I did mention that although here we start with the second order problem, higher order problems are also just as accessible, maybe not easily, but they're just as accessible with this method. So here we're going to take a look at a third order problem and see how that's done. It's going to follow the same procedure. There really is just one major difference. So let's go with this one. All right, so first of all, same as before, we start by finding our complementary solution. Okay, so we're going to find y sub c. That's going to be the solution to y triple prime plus y prime equals 0. We could write this as m cubed plus m equals 0. That would factor as m times m squared plus 1 equals 0. And so we would have three different solutions here. We would have m1 equals 0. And then here, since I've got m2 and m3 are both equal to I and minus I, we're going to have complex solutions to this one. So remember how that works. Here I want to say m2 is equal to 1i, which I'll write that as 0 plus 1i, because here we have real plus imaginary. And then m3 will equal to 0 minus I. Okay? So now we can go ahead and write our solution here. So our y sub c is equal to, I'll have c1 e to the 0 plus c2 e to the, now here, whatever the real part is, that'll be the power on your exponential. And then whatever the imaginary part is, don't include the I, just the coefficient here. This is 1i. That's going to be the coefficient on the argument of your trig function. So this would be cosine of 1x, because that's 1i. And then plus c3 e to the 0 sine of 1x. Right, so whenever you have complex coefficients, the real part is the power on your exponential, and the imaginary part, not the I, just the 1, is going to be the coefficient in the argument of your trig component. And so here we can clean that up as, well, e to the 0 is 1 every single time. So we can write this as c1 plus c2 cosine of x plus c3 sine of x. So there's our complementary solution. Okay, so now the next thing we want to do is we want to find our Wronskian. And I remember how the Wronskian works. We're going to go ahead and take the elements here of our fundamental solution set, basically these, but without the C1, C2, and C3, and we're going to write them along the top. That's going to be 1 cosine x sine x. And now take derivatives. Since you now have 3 columns, you need to take 2 derivatives so that you'll have 3 rows, just like you have 3 columns. Here, however, this gets easy because the derivative of 1 is 0, and the derivative of 0 is still 0. So a lot of these are going to be 0. Here, the derivative of cosine of x is negative sine x. The derivative of that is negative cosine x. Here, the derivative of sine x is cosine x, and the derivative of cosine x is negative sine of x. Okay? And now you find your determinant. There's several ways of finding a determinant of a 3x3 matrix. Some people like the cross-hatching method. That's fine. Some people like the Minor's method, where you take the, you got the plus minus plus thing like that, and you take the minor matrix and take that determinant. Some people like, what is that method called? It's called like Kramer's method or something like that. You see it a lot in physics. Whatever your method of finding a determinant is, that's fine. Personally, I prefer the cross-hatching method, so that's one I use, but whatever. Here, find the determinant however you like. Here I'm going to go, if I multiply these, I get positive sine squared of x, plus, if I multiply these, cosine times 0, that's 0. And then if I multiply these, I also get 0. Minus, now I go this way, I'm going to multiply these, and I'm going to get negative cosine squared of x. And then 0, and then 0. Okay, so that's going to give me sine squared of x. That when I multiply those, there was a negative there. So that should be minus a minus. So that'll be plus cosine squared x. And by the Pythagorean identity, that's 1. So my Wronskian is 1. Okay, then I have to take my W1. And W1 is, you're going to replace the first column with 0 on top and the input function on the bottom. You say, well, wait a minute. Before, there was it was only a 2 by 2 matrix, right? So when you said put the 0 on top, there was a 0 and then an F. But over here, it's a 3 by 3 matrix. So what do I do there? You just replace everything with zeros except for the bottom one. If it was a 4 by 4, 5 by 5, 6 by 6, they all work the same. It's zeros all the way down, and you just put your input function at the very bottom. So here, W1 will be 0, 0 tangent of x. And then all the rest of these stay the same. And so let's see, that's going to be 0 cosine squared x tangent of x. So 0 plus cosine squared x tangent of x. And then 0 minus, and then if I go back the other way, that's 0, 0, and negative sine squared x tangent of x. Okay. So here that's double negative is a plus. So I get cosine squared of x plus sine squared of x. And both of those are being multiplied by tangent of x. I factor out the tangent of x for both of those. But since that's the number 1, I just get 1 tangent of x. So there's my W1. I'm going to need W2 and W3 as well. So as I mentioned earlier, these get big real fast. 1, 0, 0. That stays the same. Now my second column is replaced by all zeros, except at the very bottom, I just put my input function, tangent of x. And then my third column remains the same as in the Wronskian, sine, cosine, negative sine of x. Okay. And here we've got 0 plus 0 plus 0. Is this going to be all 0? Minus 0, 0, 0 minus, no, that one's not 0. So I've got cosine x tangent x. Cosine x tangent x. And then 0, and then 0. So here my W2 is going to be negative cosine x tangent x. Let's see. Well, tangent of x is sine of x over cosine of x, isn't it? So here that's going to be negative cosine x times sine x over cosine x. And now the cosines divide away, and I just get negative sine of x. Okay, so here's my W1. Here's my W2. Sounds like I'm doing my taxes. I don't think I'll get to W4, though. All right, so now my W3. Again, first column stays the same as in the Wronskian matrix here. Second column stays the same as in the Wronskian matrix here. Third column is replaced with all zeros, except the input function tangent of x goes at the very bottom. And let's see what we get there. Okay, I've got negative sine x tangent x. Plus 0 plus 0. Minus, and then I've got 0, 0, and 0. Okay. All right, so I've got just negative sine x tangent x. Oh, let's see. Tangent of x is sine of x over cosine of x, and that won't cancel. So that one I have to leave the way it is. Okay, so there we go. That's our W1, our W2, and our W3. And now we can integrate. Good times, yeah. So now we're going to find our U1, which we take W1, divide by W, and integrate with respect to x. Let's see, our W1 was tangent of x. Okay, that's tangent of x. Over, our Wronskian was just the number 1. So tangent of x over 1 gets integrated with respect to x. Okay, so that's just integral of tangent of x. Don't you dare say secant squared of x. That's the derivative. That's a really common mistake. People say, oh, tangent, that's secant squared, right? No, that's a derivative. The antiderivative is, hopefully you remember this from your Cal 1, yeah? Tangent of x, that's going to be negative the natural log of the cosine of x. It should be, again, absolute value, but we run into issues whenever we have something that's undefined because our solutions are supposed to be continuous. And here, natural log of cosine of pi over 2, for example, would not be continuous. So here we don't put the absolute values on there since those are not going to be continuous through the zeros. Okay, so I've got negative natural log of the cosine of x. Remember, secant squared is the derivative, the antiderivative. Remember your Cal 1. Your U2 is going to be the integral of W2 over W. Okay, let's see. Our W2 was just negative sine of x. Integral negative sine of x over 1 dx, which is integral negative sine of x dx. And that's cosine of x. Again, all of these technically have a plus c on the end, but we don't need an entire family of these factors. We simply need a single version, a single copy. So we're going to set all of these to 0. If you set it to a different number, that's fine, but 0 is the easiest. Okay, let's see. And then I've got a U3 here, which is the integral of W3 over W dx. And so that's an x right there. And so that's going to be the integral of, what did I have? Negative sine of x tangent of x. Negative sine x tangent of x. It is over 1, but again, that's not really doing anything, right? You're dividing by 1. Okay, so let's see. I need to integrate this thing here. Oh, what can I do with that one? Oh, I know what I can do. I can use a Pythagorean identity on that one. Here, I'm going to write this as, so tangent of x is sine of x over cosine of x. Now, I'm multiplying that times another sine of x, so the top gets squared, and I have a negative out in front. Okay, so now here, instead of sine squared of x, I can use a Pythagorean identity to write this as, I'll leave the negative out in front. Sine squared of x is 1 minus cosine squared of x. Cosine of x. Here I can distribute the negative. That turns this negative into a positive. It turns the 1 into a negative. So I end up with cosine squared of x minus 1 over cosine of x. And now I can split it up. Cosine squared of x divided by cosine of x is cosine of x. And then minus 1 over cosine of x, that's secant of x. And now each of these are ones I remember from Cal 1. The integral of cosine of x, that's sine of x, minus, and then the integral of the secant of x is, that's going to be negative natural log of the absolute value of the secant of x plus the tangent of x. Again, plus c, but again, we're going to make that 0. Okay. And that's the hard part. So now we're done with just about everything here. So now we have that our y, I grabbed the wrong pen there, didn't I? Oh, now that we have that our y sub p, our particular solution, that's going to equal to u1 times y1 plus u2 times y2 plus u3 times y3, where u1 was negative natural log of the cosine of x. And then y1 was, I got to go back to my last page here. My y1 was just 1. y2 is cosine, y3 is sine of x. So that's going to be times 1 plus, I'm going to have y2, which is cosine of x, times cosine of x, plus, and then this one's going to be sine of x minus natural log of the sine of x plus the tangent of x times sine of x. So our y1, y2, and y3 were 1 cosine x and sine x. Our u1, u2, and u3 were the solutions that we found to these integrals, the antiderivatives we found with these integrals. And now we can clean this up a little bit. That's cosine squared, and that's sine squared. So here I'm going to write this as minus natural log of the cosine of x plus cosine squared x plus sine squared x minus sine of x times the natural log of the sine of x plus the tangent of x. Oh, sorry, I wrote sine, didn't I? That should be secant of x. Natural log of the secant of x plus the tangent of x. Just like that. Here, this is the number 1. So we can write that as negative natural log of the cosine of x plus 1 minus sine of x natural log of secant of x plus tangent of x. Like that. Ooh, forgot to close my parenthesis there. And so our general solution, our y, is going to equal to, we're going to now take our complementary solution from the very beginning here. That's going to be c1 plus c2 cosine of x plus c3 sine of x, like that. One thing to notice right here is that this number right here, this plus 1, is already accounted for. In your complementary solution, you already have a constant. So like, let's say this constant was meant to be 20. Okay, well now it's 21, but you know what? That's still a constant. If this constant was meant to be -4, well now it's -3. But so what? It's still a constant. So this, the way we say it is that this term gets absorbed by the complementary solution. You say, well, so if I put a plus 1 over here, that's going to be wrong? No, but it's redundant. No one ever writes it separately because it's already included here. So here we're going to say this is absorbed by the complementary solution. Complementary solution is a long thing to write. It's absorbed by y sub c. But these are unique. They don't exist. We don't have those terms over here anywhere. So those we just tack on. So that's going to be minus natural log of the cosine of x minus the sine of x times the natural log of the secant of x plus the tangent of x. And that would be our solution. And here you see the main difference between a second order problem and a third order problem via variation of parameters, and that's just the more variables you have, the more elements you will have in, the greater your power, the more elements you'll have in your fundamental solution set, which means your Wronskian will have more columns, 1, 2, 3 columns, which means it'll have to have more rows. The W1, W2, and W3 must match that in size. If this is a 3x3, these are all 3x3s. And when you replace a column, either the first column for W1, the second for W2, or the third for W3, you replace zeros all the way down, except the very last element of that replaced column will be your input function. So if this was a 4x4, a 5x5, a 6x6, it would work exactly the same. You would find your Wronskian, you would replace the first column, the second column, the third column, the fourth column, the fifth column, whatever, however many you had, one at a time, and find those determinants. You'd integrate every single one of them with respect to x to find your u1, u2, u3, u4, u5, however many you need, and then u1, y1 plus u2, y2 plus u3, y3 plus u4, y4 plus ... will give you your particular solution. And as always, your final result is going to be your complementary plus your particular. And that is our result. So that is the end of our section. If you have any questions, comments, or problems, please let me know. Otherwise, I hope everybody has a nice day.